at Stanford University.
Okay, let's begin. Let's begin tonight. I want to just go through a very quick review of some equations, then I want to move on. Tonight I hope to get to some physics and to discuss gravity, if nothing else, in a uniform gravitational field. We've already talked, of course, about a uniform gravitational field. That's just the, well, you all know what that is, just near the surface of the Earth. But the question is, how would you describe that uniform gravitational field in general relativity? Okay, we want to get there. We want to understand what kind of metric it describes, or describes it. But let's just write down some, just to remember some equations, just to have some review. First of all, we talked about covariantly differentiating. The idea, covariant derivatives act on tensors, in particular on vectors, and we worked out the covariant derivative as it applies to particular tensors. In particular, first of all, the covariant derivative, let's call it dm. The covariant derivative of the metric itself is always 0. Oh, let me say one more thing about the covariant derivative. The point of the covariant derivative is to write a tensor such that, I get this straight, such that in Gaussian normal coordinates, it is just the derivative. In Gaussian normal coordinates, the coordinates which are closest to Cartesian coordinates at a particular point in the space, the covariant derivative is just the derivative. But in other coordinates, it takes on a more complicated form if we want it to be a tensor. All right, so the covariant derivative.
Question about Gaussian normal coordinates. So I was searching on the web and found things that said they're the same as synchronous coordinates, and showed that basically the spatial coordinates aren't coupled with time in the metric tensor. And that's what they said about it. Is that
you know, I may be using Gaussian normal coordinates in too restricted a sense. What I mean by Gaussian normal coordinates, I may be using the term too restricted a way. The only trouble is it's the only term I know. Let's call them the flattest possible the most Cartesian coordinates at a point. All right, can you make a can somebody make a a series of letters out of that? The most Cartesian coordinates at a point.
What does the most Cartesian mean?
All right, it means exactly what we said before, that the metric at that point is a Kronecker delta, and its first derivatives are 0. Okay, that's what I mean by the most Cartesian coordinates at a point. I may be misusing the term Gaussian normal coordinates. My education was not left something to be desired, and I sometimes use terms inappropriately. Okay, we'll just call them the best coordinates. They are the best coordinates at a point. The best coordinates at a point have derivatives equal to 0 have the metric having derivatives equal to 0. And the problem of finding a tensor which, in the best coordinates at a point, reduce to nothing but the ordinary derivative is the covariant derivative. All right, so here's the covariant derivative. It acts on any component of the metric and always gives 0. Why? Because in the best coordinates, the derivative of the metric is 0. Okay. Now, next, we considered the covariant derivative of a vector. dr vs, and I chose to study a vector with covariant components. It's a covariant derivative of the covariant vector. Right? And here's what we found it is. It starts out as just the derivative of Vs, and then has a term which would be 0 in the best coordinates at a point. All right, what is it? It's plus gamma r s, let's call it p vp. Remember the summation convention? We're summing over p here. Oh, yes. Is it plus or minus? I believe it's minus. It's minus. And the minus is a convention. And we worked out what these symbols are. The gamma PRS, they are not tensors. They're made up out of derivatives of the metric. That means in the best coordinates, they're 0. They're 0 at a point in the best coordinates because the derivatives of the metric are equal to 0. But if they were a tensor, then they would have to be 0 in every coordinate, and they're not. All right, so these gammas, let's write them down. Gamma PRS is equal, gamma PRS is equal to GPN. Remember, GPN is the inverse metric, the metric except with upper components, times partial of G NR with respect to XS plus partial of G NS with respect to XR minus partial of G, oh, there's a factor of 2, excuse me, a factor of 2, minus partial of GRS with respect to XP. Shouldn't take you too, this should be memorized. It doesn't take too long to memorize it. If GPN, okay, that's just to raise some index here, but now you look at it, it has GNR, it has GNS, and it has GRS. Whoa, wait, did I do this right? No, GRS with respect to P. No, with respect to N. N. There it is. Now I have it right. It has all three combinations of G, blah, blah, with respect to X, fla, fla, and they come in three combinations, 2 of them positive, 1 of them negative, and a half here. Right. That's the Christoffel symbol with 1 upper index and 1 lower index. And that just goes right into here. That tends to make covariant derivatives rather complicated objects. You know, if I wrote down a metric for you, it's a nuisance to write all these things down, but this is what it means. All right, next, let's talk about covariant derivatives of vectors with contravariant components. All right, let's let's call it dm Vn. dm Vn. Right? As always, it starts out with a simple derivative. But I'm not going to work it out for you. I'm not going to work it out. You work it out the same way you worked it out for covariant derivatives of covariant tensors. But there's a simple trick. You can do it yourself. Do it at home. I'll tell you what the trick is. You begin by writing Vn with upper index as equal to Gn, now give me another letter, P, Vp. Okay? And now you say, I want to construct a covariant derivative of Vn. And since the covariant derivative is a derivative, it's a derivative in the best frame. It is a derivative. It will satisfy here. This is a product. This is a product of 2 things. And it will satisfy covariant derivative of GNP times VP plus GNP times covariant derivative of VP. Let's put an index down here, M, and a bracket around here. What this says is simply that the derivative of a product is the sum of two terms. The derivative of the first term, that's this one, times VP, plus the derivative of the second one times G. This holds for covariant derivatives. It holds for just about every kind of derivative you can ever think of. And now, what do we know about the derivative of the metric? Now, this is the metric, the covariant derivative of the metric. Remember that the metric in the best coordinates has no derivatives, right? So in the best coordinates, the metric itself with lower indices is constant, at least to first order, at least to first derivatives. That means the inverse tensor, the inverse matrix, is also constant to first derivatives. And so one can also argue that the covariant derivative of the metric tensor with two contravariant indices is also 0. We know how to differentiate a thing with lower indices. That's this formula over here. If you just plug that in here and manipulate it a little bit, you'll find out how to differentiate, how to covariantly differentiate a tensor with upper indices. I'll write the formula for you. Here it is. It's the same kind of thing as up here. Derivative with respect to m of Vn, derivative with respect to xm of Vn. They always start out that way. And then now plus. This you'll work out by doing this little exercise here. It's a simple little exercise, takes a few minutes. And now it's plus gamma m n, let's call it P, I guess. What did I call it? I'd like to keep my notation consistent. NMR, no, yeah, R, VR. Okay, let's look at it for a minute. As before, it begins with just a simple derivative. Then it has a term which would be 0 in the best coordinates, because in the best coordinates, the gammas are all 0. This would be 0, but it's not 0 in general coordinates. This has one lower index here. It has one upper index, has the same upper index here. Here it has a lower index contracted with an upper index. So the formula makes sense. It satisfies the rules. Upper indices contracted with lower indices, summed over, and indices generally in place. It's plus. It's plus. It's plus. That's the little peculiarity that you get by doing this exercise. It's plus. That's all you really have to remember, that when you go from covariant to contravariant, the way the indices fit together, you can't mistake it. A lower index and an upper index, that same lower index has to appear on this side. There's nothing else it can be but the lower index of the Christoffel symbol. The upper index has to appear here, and then there has to be a contraction. Okay, that's the covariant derivative of the contravariant components of a tensor. Good. Now we come to an idea called parallel transport. We've already more or less spoken about it, but let's spell it out in detail. Supposing you have a curved space. Oh, I should write down one more thing, just to write it down for now. The curvature tensor. I think I won't. We won't need it too much tonight. We won't need it too much tonight. All right. And now we have some vector field. Let it be a vector field living on the space. And I'm interested in knowing whether when I move along here, whether the field stays parallel to itself, whether the vector field stays parallel to itself. All right, so I have some vector at each point here, at each point along the curve, and I want to know whether the field stays parallel to itself. All right? Parallel to itself means that the covariant derivative is 0 along that direction. That's what it means. Covariant derivative is the difference between the vectors except written in the best coordinates. If the derivative of a vector from one point to another is 0, that vector is maintaining a relationship of being parallel to itself as you move along. Okay, so that's actually a definition. But let's see, we have written down, I'm going to write down again the covariant derivative because we're going to use it. dmvn. Let's write that down for the moment. Is equal to partial of vn with respect to xm. I'm going to write it down again. Plus gamma n mr vr. Okay, that's the covariant derivative. Now, I want to consider the derivative along the trajectory here, or along this curve, how the vector changes from point to point. That simply corresponds to taking the covariant derivative, Vn, and multiplying it between these 2 points by dx, let's see, dxm. If I differentiate with respect to xm and then multiply by dxm, that can just be called the small change in the vector going from point to point, from dx, except keeping track of the fact that the coordinates themselves may bend as you go from point to point, and that's why you have to use the covariant derivative. This is the change in the vector v in going from one point to its neighbor. What is it equal to? Let's just give it a name. dvn. It's a small change in the vector going from one point to a neighboring point. More precisely, it's the small change in the vector in the best coordinates. Okay, that's it. Now, what is that equal to? It's equal to dvn by dxm times dxm. I'm simply multiplying this equation by dxm, and then plus gamma m r n vr dxm. I did nothing here except multiply this by dxm and then sum over m. So let's erase the middle expression here. This is the covariant change in a vector going from one point to another. Now, this thing here, that's simple. That's just the derivative of something with respect to x times dx. That can just be called the differential change in v. That's the differential change in v. So look at this equation. The covariant differential change in v is the ordinary change in v plus this Christoffel symbol multiplied by dx. This is the formula which tells you how a vector changes from point to point. Now, supposing I'm interested in defining a vector which is parallel to itself as I move along this curve. Parallel to itself means it doesn't change as you move along here. At each point, you erect some best coordinates. In those coordinates, you test whether the vector is changing. If not, you say, all right, good, the vector is constant along a little segment there. Go to the next segment. Erect best coordinates at that point. Do the same thing. If at every point the change in the vector is 0, if this equals 0, the vector is said to be parallel to itself along that curve. As you move along that specific curve, the vector maintains a relationship of being parallel to itself.
The best coordinates are always parallel to themselves?
Are always what?
Parallel to themselves?
No, not necessarily. Once you find the best set of coordinates, you can rotate it. No, they don't have to be parallel to the curve, but they have to be fixed and well-defined. But they could be parallel to the curve. The best coordinates are not unique. Just like an ordinary flat space, the Cartesian coordinates are not unique because you can always rotate them. You can also rotate the best coordinates, right, at a point. And that's not important. That won't change whether your vector stays parallel to itself. All right. Moving a vector from one point to another such that this covariant differential change is 0 is called parallel transport of the vector. If you move a vector along a curve in such a way that the differential change in its contravariant component plus the Christoffel symbol multiplying v times dx along that trajectory, that being 0 is called parallelly transporting a vector along a certain curve. Okay? Now, the funny thing about curved spaces is if you take 2 points and you start a vector over here and parallelly transport it along this curve here, you'll get some other vector here. But if you choose some other curve and parallelly transport it, in general, it will come out different. So the notion of parallel transport is relative to a particular curve. This is what I showed you about cones. When we talked about having a cone with a round top or something like that, if we parallel transport a vector from here to here versus transporting it around the back of the cone, you will get a different final result. So parallel transport.
One question.
Yeah. And of course, when that happens, it's because there's curvature in between.
So I know I'm misunderstanding, but tell me where I'm wrong. I'm thinking this v, this vector, is a vector field.
Okay. What I said was for a vector field, but now just imagine that you could imagine that there was a vector field, or you could just imagine that the vector field was only defined along the curve. In fact, we don't even have to, we can even ask, how do we construct a vector along this curve such that it's everywhere parallel to itself along the curve? What we do is we solve this equation. We solve the equation that when we move the vector, we move it in such a way that this cancels this.
So my question is, if it were a vector field, then it would be independent of the path.
Yeah, well, you might, sure, the vector field would be independent of the path, but there might be one path along which this vanishes everywhere, and another path along which it doesn't. When you get to the end, you have a unique answer, but one transport of the vector, you would say that the vector was covariantly constant along one curve and not covariantly constant along another curve. Now, you're right, we're defining something slightly different. Instead of saying there's a vector field, let's just suppose we start with a vector over here. And now I'm going to fill this curve up with vectors. Let's imagine it's been filled up. So roughly speaking, there's a vector field now along this curve. Let's not worry about what it's doing over here. And then just require of this vector field along the curve that it's covariantly constant. And this is the equation that says that.
Question?
Yeah.
This isn't the main focus, but are you also preserving the length of that vector?
Yeah. That's right. Covariant, yes. Then you can prove that this equation conserves the length of the vector. I didn't assume it, but one could prove it from here. Yeah, that's right.
The reason why you didn't choose the sharp edge is because to maintain the differentiability, is it?
Say it again?
The cone, you didn't make it very sharp. It's because to maintain the differentiability.
Yeah, but it wouldn't have mattered, even if I made a sharp cone. If I want to specify what the curvature is in here, then I better make it nice and rounded so that it has a finite curvature. The curvature at the tip of a sharp cone would be infinite, so I wanted to avoid that. Yeah.
The tangent vector of that curve,
Yes.
is it always parallel?
No. But when it is, the curve is a geodesic. That's exactly what we're coming to now. All right, so we've defined let's see what's going on here. let's take the cone, slice it, and open it up on the blackboard. Okay, so it's, let's see, we're going to slice it and open it up. So it looks something like this. It's empty out here. All right. Now let's take a curve that just goes around like that. That corresponds to exactly the kind of curve that I drew over here, right? Goes around and comes back to the same point over here. This point and this point are the same point. Okay, now let's take a tangent vector, as you said. It's pretty clear that this tangent vector is changing. What would a vector which didn't change look like? A vector which didn't change would look like this, like this, like this, like this, and we come back to here. We come back to this direction over here. So the answer is no. In general, the tangent vector to a curve is not covariantly constant. But in fact, this is not a geodesic. This is not a geodesic of a cone. In fact, you can see, just flatten everything out. This is a circle. It's not a geodesic. It's not the shortest distance between these 2 points. Shortest distance between those 2 points is that. Drawn back on the cone, it would look something like this, the shortest distance between those 2 points. Okay, so now we want to get right to what you said. Question of the tangent vector and the notion of a geodesic, and just to say it, since you've already said it, or since I already said it, the notion of a geodesic is a curve. One can define it in 2 ways. You can define it as being the shortest distance, the shortest curve between 2 points. Better yet, a curve whose distance is stationary. It could be the longest distance between 2 points. If the distance is stationary, then we will say that the curve is a geodesic. But a better, not necessarily a better definition, in fact, I think it is a better definition, though. A better definition is to look locally along the curve and require that the curve be as straight as possible. Okay, now what does that mean? I'll give you some intuitions, and I'll give you a precise statement. If at each point along the curve, the derivative of the tangent vector is 0, then that curve is as straight as possible. Okay, but let's think what this means. I'll give you a intuition. I'll try to give you an intuition for it. Suppose you have a curved terrain. Now, this is a 2-dimensional example, but there's nothing particularly 2-dimensional about the notion of a geodesic. Now, let's suppose you have a car that you drive on this terrain. Okay. Also assume that the size of the car, in particular the distance between its wheels, is small by comparison with any curvature. In other words, the car is very small compared to the hills and the valleys and so forth. And now, take your steering wheel and point it absolutely dead ahead, straight. Okay? And start driving. Don't turn the wheel. Make sure in advance that it was pointing, go to your mechanic, tell him to set it straight ahead, and don't deviate. Just go straight ahead. The curve that you will execute on this space will be a geodesic. Another way to say it, the same thing, is that the tangent vector along the curve is constant. The tangent vector along the curve is constant, so let's define the tangent vector. Here we have here we have a curve. And now go to a point. We're going to construct a tangent vector right at this point and take a neighboring point. It's separated by a little interval called dxm, okay? small interval, and now draw a vector through those 2 points. Make that vector be a unit vector. And then take the limit in which the second point approaches the first point. That's called the tangent vector. Now, I need one more equation here. Remember that ds, well, okay. No, let's, no. Okay. The way that you construct the tangent vector is very simple. Tm is equal to dxm divided by something, divided by the distance between those 2 points. Just divide by the distance between those 2 points, and that's what we call ds. Remember what ds is? ds squared is the square of the distance, gmn dxm dxn. Just divide it by ds. That defines a unit vector. You can prove that it's a unit vector. I'll allow you to do that. It's a unit vector at every point along the space, along the curve. It's called the tangent vector, and it points in the direction between 2 neighboring points, the direction specified by 2 neighboring points, and its length is 1. Okay. So that's the notion of a tangent vector. And now what about the notion that the tangent vector is constant? That's the statement that if I plug in the tangent vector for v, the right-hand side or the left-hand side of this equation should be 0. So let's write that equation down. Okay. Plugging in t into that equation, it says that d tm let's call it tn plus gamma mrin tr dxm. Let's see what I did. All I did was plug in for v, t. You have a dv and a v. Here you have a dt and a t. And set that equal to 0. Go along each point and check whether as you move along this curve, this quantity is 0 everywhere along the curve. If it is, the curve is a geodesic. It corresponds to setting your steering wheel dead ahead and moving in as straight a line as you can. Okay. That's the notion of a geodesic. And we can write it in a little neater form. We can write it a slightly neater form. Let's divide both sides of the equation by ds, by the little distance between neighboring points here. All right. We're differentiating, which means we've taken a little interval here, dx, and now we're going to divide it by ds. That says that the derivative of tn with respect to distance along the curve, this is the derivative of the tangent vector with respect to distance along the curve, plus, well, let's write it equal to minus, is equal to minus gamma nmr tr, but then dxm by ds. What is dxm by ds? Tm. So I have a little equation here that only involves the tangent vector. It also, of course, involves the Christoffel symbol, but let's suppose we're given that. Let's suppose we're given the Christoffel symbol. Then the equation of motion of a geodesic is just this equation. Gammas are made up out of the metric. So if we know the metric, we know what to put on the right-hand side. And we can say one more thing. Since t itself is a derivative, we can write this as a second derivative. d second xn by ds squared. I've written now that tn is the xn by ds and then differentiated it again, ds squared. The second derivative of xn along the curve is equal to minus gamma n mr tr tm. Does this look like anything familiar? Probably not, but it is actually. If we were to think of s as time along the curve, some measure of time as we move along the curve, then this thing would be acceleration. Second derivative of the position with respect to time, if we imagine that s is like time. We'll come back to that. All right, so if s were like time, or if s were increasing uniformly with time, then this would be the acceleration. Acceleration is equal to something that depends on the metric, and some more t's here. We'll deal with them later. This has the look of a Newton equation. Acceleration is equal to something that depends on the gravitational field. The metric is the gravitational field. Right? So this is the equation that replaces Newton's equation, as we'll see, for the motion of a particle in a gravitational field. In other words, in some sense, a particle in a gravitational field moves in the straightest possible trajectory. Now, it moves through the straightest possible trajectory through space-time, not just through space. So now we have to come to space-time. So far, we've just been studying the mathematics of curved spaces. Curved spaces, as Riemann would have understood them. The mathematician Riemann was the one who invented most of this mathematics for curved spaces. These are ordinary curved spaces in which distance was governed by the Pythagorean theorem, all right? And always the square of the distance was always positive. Minkowski space is a space which also has a natural measure of space-time distance along curves, so space-time distance between neighboring points or even distant points. Minkowski space is a space with a notion of distance between neighboring points. In fact, a notion of the square of distance. Distance is usually defined in Riemannian geometry in terms of its square. Okay. In Minkowski geometry, again, we have a notion of square of distance between neighboring points, and what is it called? The proper time between the points. The proper time. Right? The proper time between the points. And it's also a notion of neighboring distance, sort of. Given 2 points in space-time, t, x, the space-time distance between them, and now let's not call it the space-time distance, let's call it the proper time, is equal to dt squared, not plus the x squared, but minus the x squared, and if there are more coordinates, let's say y and z, it would also have minus dy squared minus dz squared. That's called d tau squared. Tau is the proper time, and it's conventional to rewrite this as minus ds squared. Sometimes you use s, sometimes tau. I'm not going to use s. I'm going to use tau. But according to convention, this is equal to minus g mu nu dx mu dx nu. Now, what does that mean? G mu nu is the metric of space-time. dx mu stands for, or x mu stands for t, x, y, and z. And according to standard convention, t is called x0, and x is x1, y is x2, and z is equal to x3. That's convention. All right, so mu and nu run from 0 to 3. This has exactly the same form, I'm using mu and nu because it's conventional when talking about space-time to use mu and nu. The only new thing is the metric tensor. Let's write down the metric tensor. The metric tensor now has a -1 that corresponds to the dt squared. Notice there's an extra minus sign here. 0, 0, 0, 0, +1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. That's the matrix or the metric tensor G mu nu. Right? How does it read? It reads minus dt squared plus dx squared plus dy squared plus dz squared. And what are all these zeros doing here? The zeros are telling you that there are no cross terms dt dx, dt dy, or anything like that. These are special coordinates. These are Minkowski coordinates, and they play the role in relativity of Cartesian coordinates. In special relativity, this is all there is to it. Okay. In general relativity, G mu nu becomes a function of space and time. Let's just call it G of x. It becomes a function of space and time, not just a function of space, but a function of space-time. But one thing, what can you say, in what way is this matrix different than delta mu nu, 1, 1, 1, 1? The answer is it has a -1 in one place. But there's also an invariant concept here. The invariant concept is this one has 1 negative eigenvalue and 3 positive eigenvalues. The metric of space-time always has 1 negative eigenvalue and 3 positive eigenvalues. We're not going to spend much time dealing with that. The equations always take care of all of that. But what does it mean that there's 1 negative eigenvalue and 3 positive? It means there's 1 dimension of time and 3 dimensions of space. I could write a metric that looked like this with 2 minus signs here. That would have dt squared, let's say, excuse me, that would have 2 positives and 2 negatives. That would be unallowed in relativity. It would correspond to a crazy space with 2 time directions and 2 space directions. Einstein realized that the metric of space-time should have 1 negative and 3 positive eigenvalues. But this is we don't need to worry too much about that. Other than that, all of the equations are the same as we've done up till now. Yeah.
Had mathematicians explored spaces like this before Einstein?
You know, I don't think so. I don't think so, not to my knowledge. You'd have to ask somebody who knows a little bit about the history of geometry, but to my knowledge, no. So I think Minkowski and Einstein, or as far as I know, the first one to explore these.
The equation you wrote for d tau squared has 3 minuses and 1 positive.
Yeah.
So it's minus that matrix.
Did I get this wrong? No, I got it right. There's 2 minus signs. These are both conventional. Minus G mu nu, right. Yeah, there are 2 minus signs there. Why? Just in order to keep my notation consistent with everybody else's. So, right. Okay, other than that, as I said, everything is exactly the same. You just, if you want to know whether the space is flat, now what does flat mean? Flat does not mean that there's a coordinate system in which the metric is a Kronecker delta. It means that there's a coordinate system in which the metric looks like this. It's the Kronecker delta except with 1 negative sign. That's the notion of a flat space-time. A flat space-time is one with 1 negative and 3 positive, but in which there do exist coordinates in which the metric can be brought to this very simple form. That's the notion of a flat space-time. And if the space-time cannot be brought to this form, then it's curved. How do you check whether it's curved? You do all exactly the same things.
Could you have 3 negative and 1 positive?
What's that?
Could you have 3 negative and 1 positive?
You could. Actually, it would be basically the same thing, but
Is there a special symbol like Chronicle Delta, but it has the one negative?
Yeah, it's called eta mu nu. And so yeah, that's a good point. When we write this, if we were dealing with these coordinates, we would write this as eta mu nu dx mu dx nu. The general equation is to put a g mu nu of x here. The special case in which you're dealing with these special flat coordinates, I told you before, don't use the term flat coordinates, in which you're dealing with these special Minkowski coordinates, which are like Cartesian coordinates, is that this is called eta mu nu times dx mu dx nu. Okay, so that's what we inherit from special relativity. This is all inherited from special relativity. Okay, are we okay? Everybody clear?
There's a minus sign missing somewhere there. There's a minus sign missing on one of the etas.
In one of the what? Oh, good, thank you. Minus. Yeah. Right. That's correct. All right, so for a while now we're going to do special relativity. In other words, we're going to deal with a flat space. We're going to deal with a flat space, and we're going to wind up looking at it in polar coordinates. Not polar coordinates as Euclid would have used them, but polar coordinates as Minkowski would define them. The purpose is to define the notion of a uniformly accelerated reference frame. Now, in special relativity, there is a bit of a problem with the notion of uniformly accelerated reference frame. If you have a bunch of points which are at fixed separation, and you start accelerating them, and you keep them at that same fixed acceleration, if they're going to accelerate with uniform acceleration, then they will maintain the distance between them. But distances are supposed to transform when you accelerate something. So if we were to just start these points moving with a uniform acceleration, we would actually discover that in the rest frame of the points, the distance between them was what, getting larger and larger? I think larger and larger. That would mean, for example, if there were strings between them, that as they start moving, in an attempt to keep their distance uniform, the string would stretch and eventually break. That's not what normally would be thought of as a uniformly accelerated reference frame. What's nice about a uniformly accelerated reference frame is not only do the distance between points stay the same, but if you had strings connecting the points, they wouldn't get stretched, all sorts of things like that. Another thing about a uniformly accelerated reference frame in special relativity, if you wait long enough, uniform acceleration will lead to moving with greater than the speed of light. Okay? So uniform acceleration, to the extent that it exists and makes good physical sense, is not as simple as just moving these points all with the same acceleration. I'm going to tell you how to construct what a relativist would call a uniformly accelerated reference frame. But to do so, I want to go back a step. I want to go back to Euclidean space and talk about polar coordinates. Because the uniformly accelerated coordinate system is the analog of polar coordinates. Okay, so let's start with ordinary space, y and x. And I want to introduce polar coordinates. Polar coordinates mean an angle and a radius. So here's a point. It's characterized by a radius and an angle. And here's some equations which you're all familiar with. Okay, you know those equations. You know that cosine squared plus sine squared plus sine squared theta is equal to 1. Which is the same as saying that x squared plus y squared is equal to r squared. Finally, two other equations. Cosine of theta is equal to e to the I theta plus e to the minus I theta over 2, and sine theta equals e to the I theta minus e to the minus I theta over 2. You can check that cosine squared plus sine squared is equal to 1, just simple identity for all possible theta. These are the basic equations governing polar coordinates. Ah, yes, in this one. Thank you. An I in that one. Very good. Okay. Now, what's the equation of a circle? The equation of a circle is just that r is equal to a constant, and there's a circle. Imagine a point moving around with uniform velocity, uniform angular velocity. With uniform angular velocity, the acceleration of that point is uniform on the circle. Okay. It's uniform, the acceleration is uniform on the circle. What direction does the acceleration point? Toward the center. Okay. But the magnitude of the acceleration is constant. Okay, now what does this have to do with relativity? Relativity, we write basically the same equations to define a uniform accelerated point. That's the light cone. What is a uniformly accelerated point in special relativity? It's a point moving on a hyperbola. It is accelerated. It's not moving with constant velocity. Constant velocity would mean it had a, that its direction would be fixed. It has no velocity over here. It's moving straight upward. This is time. This is x. At this point, the velocity is 0. At this point, it's moving forward. As it moves up and up and up, it gets closer and closer to the speed of light, but never exceeds it. Okay? And the question is, what is the equation? What's the analogous equations for hyperbolas, basically? This is a hyperbola. All right, so let me just write them down. Cosine and sine theta are replaced by the hyperbolic versions, hyperbolic cosine. And let's call the hyperbolic angle omega. Omega is what increases as you move along the hyperbola. It's a kind of angle, and it plays the role of the angle in Euclidean space here. It's measured off along the curve here, along the hyperbola. This is hyperbolic sine of omega. The definition of hyperbolic cosine and sine is very similar. This is equal to e to the omega plus e to the minus omega all over 2. Very similar to this, to that one. And this one here is e to the omega minus e to the minus omega over 2. The symbol over here means divided by 2. No I in this one. No I in hyperbolic geometry. You can check, very easy, that cos squared omega minus sinh squared omega is what? 1. Sinh. It's called sinh. Analogous to this equation. And now define x, say it's the analog of this equation over here. X is equal to r cos omega and t, and t, the vertical coordinate, is equal to r sinh omega. These actually define r and omega. These are the definition of r and omega, if you like. It's a coordinate transformation. It's a coordinate transformation from ordinary x and t, flat space x and t, or just Minkowski coordinates x and t. It's a coordinate transformation to r and omega. Which one do you think is like time, omega or r? Can you tell? Well, if you're on this horizontal axis where cos omega is just 1, on the horizontal axis, cos omega is just 1, if you increase r, you're just going out along this axis. So r is like a space coordinate. Okay, you're just going out along this axis. If you increase omega from this point, you're traveling upward in analogy with traveling around the circle. Traveling around the circle, the analogy is moving upward along the hyperbola. So omega is like time, is a time-like coordinate, and r is a space-like coordinate. Now, just as there's a uniformity to the circle, at any point you can define r, and it's constant on circles, you can define r, in this case, is constant on hyperbolas. All right? So here's the hyperbola r equals 2. Here's the hyperbola r equals 1. Here's the hyperbola r equals 3. And finally, if I take x squared minus t squared along one of these hyperbolas, it's just given by r squared times cos squared minus sinh squared, but that's just 1. So a hyperbola is, a hyperbola is just fixed r, constant r, let omega vary, let the angle vary, and that defines the hyperbola x squared minus t squared equals r squared. So that defines coordinates. Those coordinates in special relativity are the closest thing that exists to uniformly accelerated coordinates. Okay. This point here moves in an accelerated trajectory. This point moves in an accelerated trajectory. The distance between here and here is the same as the distance between here and here. That you can check. Is the same as the distance between here and here. That means that as the frame, as the Lorentz frame of reference rotates, not rotates, but accelerates, as the Lorentz frame of reference accelerates, the distance between neighboring particles, let's think of these as a sequence of particles, the neighboring particles stay the same. What's unusual here, and different than an ordinary accelerated frame of reference, is that the acceleration along these trajectories is different. Let's look at a trajectory which comes in very, very close in here, very small r. It makes a sudden change of direction. A sudden change of direction. That indicates that this trajectory has a much larger acceleration. Incidentally, the accelerations, the proper acceleration, the actual acceleration that an observer would feel everywhere along this trajectory is uniform. Same acceleration here, as here, as here, as here. Just in the same way that a particle moving in a curve here feels the same acceleration inward as here, as here. The acceleration along the trajectory is uniform. The proper acceleration. What does a proper acceleration mean? It means the acceleration felt by somebody over here. You know, how much of a push he feels being accelerated over here. It's uniform along these things, along these hyperbolas. Everywhere is the same, but the acceleration is different here, 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 and here. The message is this, that if you want to define uniform acceleration, you have to have acceleration which is constant in time is okay, but you're necessarily going to have different accelerations at different points of space, at different r. This never exceeds the speed of light, and the proper distance between points stays fixed. Remember, proper distance is, yeah.
The omega here is not an angle, it goes from minus infinity to infinity.
That's right, it's called a hyperbolic angle. It's called a hyperbolic angle, and it is not an angle. It's not an angle, it doesn't go from 0 to 2 pi. That's exactly right. It goes from minus infinity to infinity. Yeah, I'll tell you what proper acceleration is. Yeah, it's the derivative with respect to proper time. Yeah. Proper acceleration would be d second x mu, not by dt squared, but by ds squared, where s would be, or d tau squared, excuse me, d tau squared. All right. That's the notion of proper acceleration. You measure the acceleration not with respect to ordinary time, but with respect to proper time. Okay. It's the rate of change of the proper velocity, which is dx by d tau, with itself with respect to tau. And it's everywhere the same along these curves, but differs from one point to another. The further out you are, the smaller the acceleration. The straighter, the less curved the trajectory. In fact, you can write an equation for the acceleration. For the proper acceleration. The proper acceleration A along such a trajectory depends on only one thing. It depends only on r. Okay, it depends only on r. In units in which c is equal to 1, the acceleration, let's take a particular curve here and call it capital R. Capital R represents its distance along here. Call it capital R, not little r, but capital R is just a particular value of little r. Then along that hyperbola, the acceleration is given by 1 over capital R. The smaller capital R, it's actually the same thing as going on here. The smaller little r, the bigger the acceleration needed to hold it in place. Okay, so the acceleration is 1 over r. Now, this doesn't make good unit sense. What's the units of acceleration? Length divided by time squared, right? Okay. Let's write that as length squared divided by time squared times 1 over length. Okay, so acceleration has units of 1 over length times velocity squared. Okay. If we work in general units, not set the speed of light equal to 1, the acceleration here is equal to c squared over r. Okay. That means that for a fixed r, the acceleration is very, very large. You have to go to very, very large r before you're talking about a moderate acceleration, because of the square of the speed of light here. Yeah, question? No, okay.
Is r the x-intercept of the curve?
Yeah, r is the x-intercept of the curve. That's exactly right. And this acceleration is exactly the acceleration, ordinary acceleration, that you would experience at this point moving on that curved space-time trajectory. Yeah. The more curved it is over here versus here and here, the more acceleration. Okay, so I'll use c equals 1 generally, but keep in mind that this acceleration is very big unless r itself is very big. Okay, let's go a little further. Yeah,
It looks like what curves you're going to get is very dependent on where you put the origin.
that is correct. That is correct. That is correct. A uniformly accelerated reference frame is defined relative to a particular origin. Okay? This, that's right.
I mean,
Yes, that's correct.
nothing should be relative to the origin. I
We
mean,
better find that no real physics depends on. I'll tell you what we're doing. We're introducing a somewhat arbitrary set of coordinates. And in that arbitrary coordinates, we're going to write the equation of motion of a geodesic. And we're going to see that the equation of motion of a geodesic looks like a particle falling in a uniform gravitational field. But only if we, really work it out in detail. Okay, so I'll show you what we're doing. We'll get there. We'll get there. Yes, you're right. This is one of many possible coordinate systems where you could put the origin any place you like. And for that particular coordinate system, we have a well-defined r and omega, but we could move the origin if we liked. But let's not. Let's not. Let's keep the origin fixed. Okay, so here is the acceleration. And now let's talk about the metric. Let's talk about the metric. First, the metric in ordinary polar coordinates. Metric in polar coordinates, ordinary distance squared, that's equal to the r squared plus what? Anybody remember? Something involving d theta squared.
R cosine theta, is that right?
No. This is not a sphere. This is not a sphere. This is just a plane. You're thinking about the sphere, right? It's just r squared. R squared d theta squared plus the r squared on the plane. This just says that for a fixed separation theta, the actual distance along here increases linearly with r. So for a given d theta, the distance associated with d theta increases linearly with r. Therefore, the square of the distance increases quadratically. This is the metric of the flat plane in polar coordinates. Now notice, first of all, that the metric is not the Kronecker delta. It has the r squared, that's 1, but it has r squared d theta squared, so that's r squared. If we were to write the metric, and a two-dimensional metric for this would look like this. Okay, now, it wouldn't be the Kronecker delta. It has this r squared here, position dependence. Why? Because the coordinates are curved. Space is not curved. Completely flat space, curved coordinates. The analog here is d tau squared is equal to r squared d omega squared minus the r squared. Now, I've taken only 2 dimensions. For the moment, I'm going to ignore y and z. We don't need y and z now. We're going to be thinking about a particle falling in a gravitational field along what is the vertical axis will be the x-axis, and y and z will be the other coordinates, and they won't matter for the problem we're going to discuss. So the problem we're going to discuss is just r and omega, time and distance from the origin. Time and distance from the origin. That's the metric. And we want to see what that metric has to do with gravitation. Gravitation is supposed to have something to do with the metric. So here's what we're going to do. Remember, as we move outward here, the acceleration is changing. If we go very, very far away, let's think about a place far enough away that the acceleration is, pick an acceleration. What's a good acceleration? How about 10 meters per second per second? Okay? Let's go out far enough out here that the acceleration is g, 10 meters per second per second. It's accelerating to the right. Okay, so where was our formula? Our formula was that the acceleration is equal to 1 over r times c squared. And we're going to set that equal to g. So that means r is equal to c squared over g. We have to go very, very far away. Measured in meters, what is c? C is 180, no, not 186,000. 3 times 10 to the 3 times 10 to the 8th meters per, and 3 times 10 to the 8th. So 3 times 3 is 10 times 10 to the 16th. This number here is 10 to the 17th. This is only 10, so this whole thing is 10 to the 16th. We have to go out 10 to the 16th meters before we find a place which is accelerating with the ordinary gravitational acceleration. Okay? But let's go out there. Moreover, if we don't move too much along the r direction, this acceleration won't change much. Right? So let's imagine we fix on a certain distance r given by this. Okay? If we set c equal to 1, of course, then this is just 1 over g. But we have to keep in mind that 1 over g corresponds to a very, very large distance. The 1 is the thing which is big. It's really c squared. Let's go out to a distance r, where the acceleration is g, and then think about a region of r which is close to r. This corresponds to being near the surface of the Earth, not allowing things to change too much. So we're going to move a little bit away from that r, and we're going to call the distance along there y. I guess I called it y, not x. All right, so the distance from this hyperbola, the space-like distance from this hyperbola is y to the specific hyperbola at that place. In other words, I'm writing that r, little r, is just equal to big R, which I'm going to keep fixed, plus y. Making new coordinates, these coordinates are sort of tailored to be around this point, which is moving with the gravitational acceleration g, the neighborhood of that point. And now I'm going to rewrite the metric. I'm going to rewrite the metric. Let's see, where can we rewrite that? Let's erase this. Just rewrite it. D tau squared is equal to r squared. That's this little r squared, but that's big R squared plus 2ry plus little y squared, right? All times d omega squared minus dr squared. So now I have an even more complicated looking metric here. Well, it's a little more complicated, not much, and here it is. But we're going to focus about the region of R. So let's divide out R from this. Let's write it in this form. 1 plus 2y over R plus y squared. Is it over r squared? Yes, r squared. I'm factoring r squared out of here, and now I'm going to multiply this r squared d omega squared minus dr squared. One last step. I'm going to call r times omega, big R, times omega. I'm going to give it a new name. I'm going to call it little t. I've called the original time here big T. I'm going to call this thing little t. Where is it? This is little t. Okay, and now I get a metric that looks like this. 1 plus 2y over r. What about this? This is much smaller than this. Remember that r is enormously big. R was how big? 10 to the 16th meters. Okay? And y, I'm assuming that y is, a couple of 100 feet or something. We're talking about falling in a we're going to be talking about falling in a gravitational field. So y is a small number compared to r. Y squared over r squared is much, much smaller. Okay. Y over r is small. Y is 10 feet or 100 meters, or how far did that guy fall?
24 miles.
24 miles. That's tiny compared to 10 to the 16th meters, right? All right, and y squared over r squared is even much smaller. So I'm going to drop this. So we did a whole bunch of stuff, and at the end of the day we get a metric that, apart from this, which is small, just looks like good old metric, dt squared minus dr squared. It just looks like space and time in the more or less ordinary way. D space squared minus d time squared minus d space squared, but with a little correction. A little correction, and that little correction is what accounts for gravitation in this accelerated reference frame. Now, first of all, keep in mind that we're really talking about flat space. So far, we have not introduced any curvature. This is really flat space. So any gravitation that we find here is, in a sense, the same fake gravitation that we find in the accelerated elevator. All right. We're studying physics in an accelerated coordinate system. It's the elevator being pulled in this direction here. And what do we expect to find? We expect to find that in that elevator there's an effective gravitational field. The effective gravitational field is associated with this over here. Okay? It's associated with this over here. And let me tell you what the connection is now, and then we're going to, well, you know, maybe instead of, instead of telling you, what we'll do is work out the equation of motion of a particle in a metric like this. All right, here we have a metric. And that's all there is to it. It's really simple. Oh, what is r again? R is related to the acceleration. Where do we write it down? We said that, that the acceleration is c squared over r. If I set c equal to 1, let's set c equal to 1, then, g. G is c squared over r. The gravitational acceleration, we chose r so that it was accelerating with 10 meters per second. That gave us this equation. In c equals 1 units, this is just 1 over r. So 1 over r is g. 1 over r is g. And look what we have. We have just 2y times g. Have you ever seen the expression y times g in studying gravitation in a uniform field? The potential energy, y times g. Actually, it's not quite the potential energy. It's the potential energy divided by the mass, but it's just called the gravitational potential, right? This is y times g is the gravitational potential, and this is 1 plus twice the gravitational potential. That's extremely general. In any kind of gravitational field, as long as the gravitational field is more or less constant with time, not doing anything too radically relativistic, this coefficient multiplying dt squared is always 1 plus twice the gravitational potential. All right, but why do I call this the gravitational potential other than that it just looks like the gravitational potential? Because if I work out the equation of motion of a particle in this metric, I will find that the equation of motion is essentially, as long as the particle is moving slowly, as long as the particle is moving slowly, as long as there's a good Newtonian approximation, as long as things are not too relativistic, then we'll see that that particle falls along the y-axis like a particle in a uniform gravitational field. All right, so here's our basic metric, and we want to find out how particles move in that metric. What's the rule for how a particle moves? Anybody know? Yeah.
First of all, isn't the r there y?
Yes, sorry, it's either r, it could be r or y. You're absolutely right. We could set this equal to y now. Why is that? Because dr is equal to dy. That's a good point. Okay, dy squared. Right, so we're writing the metric in the y-t coordinates. This is only good for the vicinity. We made some approximation here. We threw away a term. We said it was very small. It's only good in the vicinity of this distance from the center. In other words, it's only good in the region where the acceleration is really g.
So a question about big R. It seems like, I mean, you picked that so that the constant acceleration curve would approach the asymptote t equals x, basically. Or, I mean, that's why you did it. This is sort of a computational trick or whatever device.
To do what?
I mean, you could have constant acceleration beginning at any point along x.
That's correct. You could. There will always be hyperbolas, but they won't asymptote to the same. That's right. That's correct. Yeah, so that's right. So there's a uniformly accelerated frame everywhere. But that's the same, that's exactly the same as in ordinary physics. There's a uniformly accelerated frame with an origin over here. There's a uniformly accelerated frame with an origin over here. In other words, it's just a bunch of different elevators whose floors are at different height at a particular instant. Right, that's all that's going on here. And we can think of this curve here as being the floor of the elevator. The elevator is being pulled in that direction now, so it's an elevator on its side. The elevator is being pulled this way. And somebody's experiencing a gravitational field and being held down. I'm sorry, you need some arms. Right, so elevator is being pulled that way. We can take this coordinate r to be the bottom of the elevator, and the height above the floor of the elevator we're calling y. Okay? Y is the height above the elevator, and here's the metric. What do I do with it? Here's the metric of space-time in the elevator, in the uniformly accelerated elevator. All right. We had to do a little bit of work to get there, but that's what it is. The metric tensor in the vicinity of a point accelerating with the speed of gravity, sorry, with the acceleration of gravity near the Earth's field. That's it. Okay, now, what are the rules about particle motion? Most of you probably know them. The rule about particle motion is that particles move on geodesics. Not geodesics of space, but geodesics of space-time. In other words, we take the metric of space-time, whatever it is, and we go through exactly these same operations. And here is the equation of motion of a particle. This is the equation of motion, was the equation of motion which says geodesic, go straight ahead. But not straight ahead in space now, but straight ahead in space-time. But otherwise, the equations are the same. Let's write them out. I want to write them slightly differently. d second x in by. Now, we don't want to, yeah, okay. d tau squared. This is called the proper acceleration. As long as the elevator is moving slowly, in other words, down here, if it hasn't been accelerating long enough to get up near the speed of light, then the proper time and the ordinary time are essentially the same, and this is just the ordinary acceleration. This could be, what would we choose? X. We would choose x to be y. We want the y component of acceleration along that direction. So this would be the y component of acceleration. That's the left-hand side. And the right-hand side is minus gamma. Now, the n component stands for y. This is the y component of motion. So we have minus gamma y for the y direction, mr, and what is t? T is dxr by ds, dxm by ds. Okay, now fortunately, there's a whole bunch of these now. M and R can run over all the possible coordinates, 1 through 4. So it looks like, well, there's basically 10 such contributions, but most of them are extremely small. As long as the elevator is moving slowly and as long as the object that we're interested in, namely the object, the particle, whose coordinate is y, as long as all of the motion is slow. then only one of these combinations is significant. How big is dt by ds for slow motion? Remember? It's essentially 1. Because s and t, or d tau, excuse me, this should be tau. Tau for the relativistic case. These are the components of 4 velocity, but the components of 4 velocity for a particle which is moving slowly, the only component that's important is the time component. The time component of velocity, what does that mean? Whoever heard of the time component of velocity? Well, it's just 1. It's just 1. It's derivative of time with respect to time. In this case, derivative of time with respect to proper time, but proper time and time are almost the same. So the 2 entries here with r and m standing for time, those are big and they're just about 1. They're both equal to 1. What about a space component divided by d tau? Well, that's proportional to the actual ordinary spatial velocity. We're assuming the spatial velocity is small compared to the speed of light. So the only important contribution here comes when r and m are time components, and that's minus gamma y time time. d second y by d tau squared is equal to minus gamma yt. That must be the gravitational force. The Christoffel symbol must be the gravitational force. Must be the derivative of the gravitational potential energy. So let's go back to the definition now. Here it is up here. Here's the Christoffel symbol that we're interested in. And what do we need? We need the one with 2 time components and 1 y component. So let's see what we get. What did I have here a minute ago? P, what was this, P? And what's down here? M and R? N and R, right? No. R and S. R and S. Yeah. Okay. And we're going to throw away some small things. Okay, so G, P, N. What is this P here? This P here is supposed to be Y. All right? So there's a G, Y something. A G, Y something. But the only G, Y something is G, Y, Y. And that's 1. Or maybe minus 1. I'm going to lose the signs because I'm getting tired. No. The GYY is equal to plus 1. So the only G that appears here is GYY. It's the only component of the metric that has a y index. All right, so this one is just 1, GYY. And what do we get here? We get partial of GY something R with respect to, what is this? These are supposed to be time components, and this is supposed to be y component. GYR with respect to time. This one is the same thing. GYR, that's 0. There is no YR component here. That's just 0. There's only one component. There's only one term, and it's this one. And if you work it out, it gives you minus derivative of G. Now let's say R and S are supposed to be time components. So this is time divided, and what is N? N is supposed to be Y. This whole Christoffel symbol is nothing but the derivative, or minus the derivative, 1/2. There is a 1/2 there. 1/2 minus derivative of the time component with respect to y with a factor of 1/2. That's what's on the right-hand side over here. I think this should be plus derivative of G time with respect to y. Does this look at all familiar, that the right-hand side of an equation of motion contains a derivative with respect to y? Potential energy, right? Force is equal derivative of potential energy. Yeah. So somehow, GTT must be the potential energy. But look at this. Here's GTT right here. Here is GTT. This term is constant. It doesn't have a derivative. But this term does have a derivative with respect to y. The derivative of this term with respect to y is just 2g. So this is just equal to, oh, is it 2? A minus or plus? There's a minus. Yeah, there's a minus that cancels. There's a half here. Yeah. The half is canceled, and there is a minus sign. I'm too tired to remember where the minus sign came from the fact that d tau squared is, this is minus GTT. Right? The derivative of GTT with respect to y is just 2g. Get rid of this half, and what is this all equal to? It's equal to minus g. That's the equation of motion of a particle in a uniform gravitational field. Okay. So we went through what is a rather complicated derivation, but what we learned is the following: that first of all, space-time has a metric, and the metric can have fairly complicated structure in arbitrary coordinates. In uniformly accelerated coordinates, it has this extra term there. And the equation of motion for a geodesic, at least as long as things are going slowly and as long as the Newtonian approximation, the equation of motion for a geodesic is just Newton's equation in a uniform gravitational field. Uniform gravitational field, constant acceleration, it's what we expected. But to do it properly using metric and using Christoffel symbols and all these things, you know, it's a fairly complicated procedure. Einstein, of course, guessed this. He guessed all of this in the opposite direction. He didn't know about Christoffel symbols. He didn't know about, he knew about uniform accelerated coordinate systems. And somewhere along here is somehow the place where he started. I don't know exactly how he started, but somehow along here, this was the observation that, that motion is geodesics, geodesics in a particular metric, and the metric of uniform acceleration just looks like this. So we've come back, we've come around sort of full circle from the first lecture where we talked about accelerated elevators giving rise to gravitation, and we've come around full circle, but so far we haven't gotten to real gravitational fields. These are not real gravitational fields because they really correspond to flat space up there. If we were to take this metric and calculate the curvature tensor, it would be exactly 0, indicating that there do exist coordinates where the metric has the simple form like this. So this gravitation that we're experiencing here is really exactly the gravitation due to an accelerated frame of reference, not due to real gravitating matter. Now we can sort of guess what the effect of real gravitating matter would be. Instead of putting 2y times little g, what's the gravitational potential in a, let's say we have a gravitating object, and again, we can use a y coordinate over here. Yeah, it's 1 over y, right. And so we can expect that when we study an actual gravitational field of a gravitating object, we're going to get Newton's constant here divided by y. And that's the Schwarzschild metric, but not quite. We're gonna work out the Schwarzschild metric. No, you made a mistake. What's the potential energy of a gravitating object? Try it again. What did you say?
Get the sign wrong.
You got the sign wrong. Right. So we get this. Oh, but that's weird. because that means that that means when y is large, this is small. Okay, that's good, because this is positive. But something crazy happens at the point where, sorry, this is not 2g, this is 2gm, the mass of the gravitating object. Something happens when y is equal to 2gm. This coefficient is just 0. Something very peculiar there, right?
Does this have to do with the approximation?
No. This has to do with the horizon of the black hole. Right. Right, so I plugged in the gravitational potential here, guessing that the same kind of thing would happen, and it does. This GTT by dy, that is just the derivative of the gravitational potential. So if we want our equations to work out and look like a falling mass in a gravitational field, we want to plug in the gravitational potential here, gm over y. But then we find something really odd. This coefficient vanishes somewheres. Okay? That vanishing is the horizon of the black hole. All right, so next time we're going to get into the subject of the Schwarzschild metric. We're not going to derive it now. We need field equations to derive it. We haven't discussed field equations yet. We've only discussed the geometry, and we've discussed the motion of a geodesic in a gravitational field. And so this is just a little demonstration of how geodesics give rise to Newton's equations. And then we jumped ahead and said, okay, let's guess that that's more general and see something like this. So immediately we discover something odd, and that oddness is the oddness of the black hole metric. Good. Okay, I think we're finished for tonight. Yeah.
Technically, that on that whiteboard, the Christoffel symbol should be eta because it's in the Gaussian space.
It should be what?
Where you have the gamma and that.
What should it be?
Should that be the eta?
No. Look, the metric is not eta. The metric has this extra term here. Now, you say, but wait a minute. The original metric, the original flat space metric was just eta. And that's correct. If you were to have done this calculation in the original flat space coordinates, you would have found no force. That's because the eta is constant and it has no derivative, has no Christoffel symbol. So if you were to work in the original coordinates, you would find no gravitational force. That's not surprising. If you're in outer space and you have an elevator and the elevator is not being accelerated, no force. Things move on straight lines in that frame. In the accelerated frame of reference, particles move on curved trajectories, and those curved trajectories are they're not really curved trajectories, but they look like curved trajectories in the new coordinates, and their motion is governed by Newton's equations with a right-hand side. You see, the fact that the Christoffel symbols are not a tensor, that's important. If they were a tensor, then if they were 0 in one frame, they would be 0 in every frame. And since this derivative is the gravitational force, it would tell you that if the gravitational force is 0 in one frame, it's 0 in every frame. But that's not true. The gravitational force in a non-accelerated frame is 0. The gravitational force in an accelerated frame is not 0. That's the equivalence principle, equivalence of gravitation and acceleration. So it's important that this thing on the right-hand side is not a tensor. If it were a tensor and it was 0 in one frame, it would be 0 in every frame. Okay, that's the idea of the value of the force in Newton's equation, depending on what frame of reference you're in. Okay. Yeah.
Can you give a little bit more feel for why we needed to have a huge R to make this?
To make the acceleration, modest. It was only in order to be working in a reasonable non-relativistic framework. Yeah, it was in order to compare with non-relativistic framework. We don't want the acceleration to be so big that in a small amount of time we get up near the speed of light. We want the acceleration, but I decided just to put in the ordinary gravitational acceleration here. Okay, so that's c squared over r. Well, that's just the way it is. If you, in these coordinates here, the place where the acceleration is modest is very far away. Okay. So, after all, the gravitational field of the Earth is pretty modest. And, you can think of a lot stronger gravitational fields, and we will talk about them. Okay.
For more, please visit us at stanford.edu.